When we first hear that the speed of light is the ultimate limit, it sounds like a statement about motion, about how fast something can go through space. But the deeper truth, the one that Richard Feynman kept pointing toward, is that this limit is not really about speed at all. It is about the structure of reality. The speed of light is not simply a very large number measured in meters per second. It is a fundamental constant that defines how the universe is allowed to behave. To understand this, we have to let go of everyday intuition and follow the logic of nature itself. In ordinary life, speed feels relative and flexible. A bicycle is slow compared to a car is slow compared to a jet, and a jet is slow compared to a rocket. From this perspective, it seems natural to assume that speed is just a matter of technology and energy. Give us a powerful enough engine, and any limit should eventually fall. But physics tells a very different story. No matter how advanced the engine, no matter how much energy we pour in, there exists a boundary that cannot be crossed. Feynman emphasized that this boundary is not imposed by practical constraints, like friction or inefficiency. It is imposed by the way space and time themselves are woven together. The key realization is that space and time are not separate, independent stages on which events play out. They are deeply connected, forming a single entity often called spacetime. The speed of light is the conversion factor between space and time, the number that tells the universe how much space is equivalent to how much time. In this sense, the speed of light plays a role similar to the number that links inches to centimeters. It is not arbitrary, but once chosen, it defines the entire measurement system of reality. This idea becomes clearer when we consider how light behaves. No matter who measures it, light always travels at the same speed. This is not because light is stubborn, but because the universe is consistent. If two observers are moving relative to each other, they may disagree about distances and durations, but they will always agree on the speed of light. To make this possible, space and time themselves must adjust. Lengths contract and clocks tick at different rates, not as tricks of perception, but as real physical effects. The universe reshapes itself to protect the constancy of light speed. Feynman loved to point out how shocking this is. We are used to thinking of space as rigid and time as universal, flowing the same for everyone. But experiments force us to abandon this view. The speed of light reveals that space can shrink and time can stretch, depending on motion. This flexibility is not optional, it is required. Without it, the laws of physics would contradict each other. The speed of light is the anchor that keeps these laws consistent. Now consider what would happen if this speed were not a limit, but just another large number. If objects could exceed it, information could travel faster than light. Signals could be sent into the past from certain perspectives. Cause and effect would lose their universal order. An event could influence another event that, in some frame of reference, had not yet occurred. Feynman stressed that physics cannot allow such contradictions. The speed of light prevents the universe from becoming logically incoherent. This is why the limit is so deeply embedded. It is not about light beams racing through empty space. It is about information, influence, and causality. The speed of light is the maximum speed at which cause can propagate to effect. It is the speed at which reality updates itself. Anything faster would break the chain that links events together in a consistent order. Energy plays a crucial role in enforcing this limit. In classical physics, adding energy always increases speed. But as an object approaches light speed, this relationship changes dramatically. Each additional unit of energy produces a smaller increase in speed. The object resists acceleration more and more strongly. From a modern perspective, this happens because energy itself contributes to inertia. The more energy an object has, the harder it is to change its motion. Near light speed, this effect becomes overwhelming. Feynman explained that this is not a mechanical resistance, like air drag or friction. It is a fundamental property of matter and energy. As speed increases, energy piles up in such a way that reaching light speed would require infinite energy. Infinite energy is not something we might someday achieve. It is a signal from nature that the question itself is invalid. The universe is telling us that this speed is not meant to be reached by massive objects. Light, on the other hand, has no mass. Photons do not experience this resistance. They always move at the same speed, never faster, never slower. They exist at the boundary itself. This is another clue that the speed of light is not just a maximum, but a defining feature. Light does not approach the limit, it lives on it. From Feynman's perspective, asking why the speed of light is the lim. It is similar to asking why angles in a triangle add up to a certain value in a given geometry. Once the geometry is defined, the result follows. In the geometry of spacetime, defined by how energy, matter, space, and time interact, the speed of light emerges naturally as the limiting speed. Change that limit, and you must change the entire structure of reality. What makes this idea so profound is that it strips away the idea of special privilege. The limit does not exist to frustrate human ambition or to slow down spacecraft. It exists because the universe requires it to function at all. Without a maximum speed, there would be no consistent way to define simultaneity, no universal agreement on what events are connected, and no stable foundation for physical law. Feynman often warned against mistaking explanation for comfort. The fact that the speed of light is fundamental does not make it feel intuitive. It clashes with everyday experience, which evolved at speeds far slower than light. But physics is not obligated to align with intuition. It is obligated to align with reality, and reality, as experiments repeatedly show, is built around this limit. When we say that light speed is not just a fast number, we are saying that it is a structural constant. It shapes the possible and the impossible. It defines what kinds of motion can exist, what kinds of communication are allowed, and what kinds of universes are logically stable. In this sense, the speed of light is closer to a rule of grammar than a speed limit sign. It dictates how the language of the universe can be spoken. Feynman's genius was not just in accepting this fact, but in showing how deeply it runs. From particle interactions to the flow of time, from nuclear reactions to the stability of matter, the same limit appears again and again. It is written into the equations not as an afterthought, but as a foundation. Remove it, and the equations collapse. So the speed of light stands not as a challenge to overcome, but as a revelation to understand. It tells us that reality has an internal logic, a structure that cannot be bent without breaking everything else. What collapses the mind is not the number itself, but the realization that the universe is not infinitely flexible. It has a backbone, and the speed of light is one of its strongest bones. When motion is slow, the universe feels simple. Space appears fixed and solid. Time seems to flow the same for everyone, and movement feels like something that happens within this stable background. This intuition is so deeply rooted in everyday experience that it feels almost impossible to question. Yet, as Richard Feynman repeatedly emphasized, this comforting picture is not how reality actually works. The moment's speed approaches that of light, space and time stop behaving like passive containers and begin to reveal their true, flexible nature. At low speeds, the differences are too small to notice. A moving clock appears to tick at the same rate as a stationary one, and a moving ruler seems to have the same length as when it is at rest. Classical physics works well in this domain, and for centuries it shaped our understanding of the universe. But nature was quietly hiding a deeper truth. Experiments involving light, electricity, and magnetism began to expose contradictions that classical ideas could not resolve. Feynman loved these moments because they showed that the universe was forcing us to think more carefully, not just compute more accurately. The turning point comes from one strange and stubborn fact. The speed of light is the same for all observers, regardless of how fast they are moving. This statement alone shatters classical intuition. If two observers move relative to each other, common sense says they should measure different speeds for the same object. This works for cars, balls, and sound waves, but light refuses to obey this rule. Every observer, no matter their motion, measures the same speed for light. The universe does not compromise on this point. To preserve this fact, something else must give way. Feynman explained that the sacrifice is made by space and time themselves. They are not absolute. They adjust depending on motion so that the speed of light remains unchanged. This adjustment is not a trick of measurement or a psychological illusion. It is a real physical transformation of how distances and durations exist. As an object moves faster, time for that object slows down relative to a stationary observer. This effect, known as time dilation, sounds abstract, but it has been measured countless times. Atomic clocks on fast, moving airplanes tick more slowly than identical clocks on the ground. Particles created in the upper atmosphere survive longer when moving near light speed than they would if they were at rest. Feynman often pointed out that nature does not care whether we find this strange. The clocks genuinely run slower. Time itself stretches. At the same time, space undergoes its own transformation. Lengths contract in the direction of motion. An object moving near light speed becomes shorter along the direction it is traveling, as seen by a stationary observer. This contraction is not caused by physical compression or stress. The object does not feel squeezed. Instead, space itself is reshaped. The ruler is not crushed. The geometry of spacetime is altered. These two effects are inseparable. Time dilation and length contraction are different expressions of the same underlying reality. Space and time are parts of a single structure. Feynman emphasized that trying to talk about one without the other leads to confusion. The universe adjusts both together to maintain consistency. As speed increases, these effects grow stronger. Near light speed, they become extreme. Time slows almost to a standstill, and lengths shrink dramatically. At the exact speed of light, the equations tell us that time would stop entirely for the moving object, and its length would shrink to zero along its direction of motion. This is not something massive objects can experience, because reaching that speed would require infinite energy. But light itself exists at this boundary. For a photon, there is no passage of time and no distance traveled in its own frame. From emission to absorption, the event is instantaneous. This realization deeply fascinated Feynman. It suggests that space and time are not universal experiences, but relationships that depend on motion. What one observer calls a long journey, another may call an instant. What one observer calls a long object, another may see as compressed. There is no single, absolute answer. Reality allows many consistent perspectives, all connected by the same underlying rules. One of the most unsettling consequences of this is the loss of universal simultaneity. In everyday life, we assume that now is the same everywhere. Events happening at the same time for one observer are assumed to be happening at the same time for all observers. But near light speed, this assumption fails. Two events that appear simultaneous to one observer may occur at different times for another observer moving relative to the first. There is no global present that everyone agrees on. Feynman pointed out that this is not a philosophical inconvenience, it is a physical necessity. If simultaneity were absolute, the speed of light could not remain constant for all observers. The universe gives up the idea of a universal now to protect the deeper consistency of its laws. As objects approach light speed, the separation between space and time becomes less and less meaningful. They blend into one another. Motion through space becomes motion through time. An object that moves faster through space necessarily moves more slowly through time. This trade-off is not optional. It is built into the geometry of spacetime. From this perspective, light speed is not just a limit on velocity. It is a boundary between different modes of existence. Below this boundary, objects experience time and have rest frames. At the boundary itself, light experiences no time and no rest. Above the boundary, the concepts of cause and effect would unravel, and the equations of physics would lose meaning. Feynman stressed that the universe is not designed to accommodate such states. The documentary-style truth behind this is that the universe is economical. It uses simple rules to generate complex behavior. The rule that light speed is constant forces space and time to be flexible. That flexibility, in turn, explains a vast range of phenomena, from the behavior of particles in accelerators to the life cycles of stars. It is not an isolated curiosity. It is a central organizing principle. What makes this idea so powerful is that it replaces mystery with structure. Instead of asking why time slows down or lengths contract, Feynman encouraged us to see these effects as inevitable. Once the speed of light is fixed, the transformation of space and time follows automatically. There is no extra mechanism, no hidden force stretching clocks or squeezing rulers. The geometry itself does the work. This challenges the way we think about reality at the most basic level. We are accustomed to thinking of space as the stage and time as the clock ticking in the background. But near light speed, the stage bends and the clock stretches. Reality becomes dynamic, responsive to motion. The universe is not a static arena. It is an active participant. Feynman often highlighted that this understanding does not make the universe less real or less objective. On the contrary, it makes it more precise. Different observers may disagree on measurements, but they all agree on the underlying laws. The transformations between their perspectives are exact and predictable. Reality does not become subjective, it becomes relational. As speed approaches light speed, these relationships dominate everything else. Mechanical strength, material composition, and internal structure become secondary. Space and time dictate behavior more strongly than any physical constraint. This is why no engineering solution can bypass the limit. The limit is not imposed by matter, it is imposed by space-time itself. The collapse of intuition here is total. The idea that space can shrink and time can slow feels absurd until experiments force us to accept it. Feynman insisted that this discomfort is a sign of learning, not failure. Nature does not owe us intuitive explanations. It only offers consistent ones. In the end, The transformation of space and time near light speed reveals a universe that is far more interconnected than it appears at first glance. Motion reshapes reality. Speed alters the fabric of existence. Light speed stands as the threshold where these effects become undeniable. What collapses the mind is not just that things change near this limit, but that they must change. Without this transformation, the universe would contradict itself. Energy feels simple when speeds are low. You push something, it moves faster. Push it harder, it moves even faster. This rule works so well in everyday life that it feels universal. For centuries, physics was built on this intuition. But as Richard Feynman loved to show, nature is under no obligation to respect human habits of thought. When speed approaches that of light, the relationship between energy and motion changes so radically that it forces us to rethink what mass, energy, and movement really are. At ordinary speeds, mass seems like a fixed property. An object weighs what it weighs, no matter how fast it moves. Energy can be added without altering the object's identity. But as motion accelerates toward light speed, this neat separation begins to dissolve. Energy stops behaving like a mere accessory and starts acting like substance. The faster an object moves, the more energy it carries, and that energy resists changes in motion. This resistance is what we experience as inertia. Feynman emphasized that inertia is not just about mass. It is about energy. Anything that carries energy resists acceleration. At low speeds, this effect is small and easily ignored. But near light speed, it becomes dominant. Each additional unit of energy makes the object harder to push, not because of friction or structural limits, but because energy itself contributes to inertia. This leads to one of the most counterintuitive consequences in physics. Adding energy does not produce a proportional increase in speed. Instead, it produces a diminishing return. Early on, a little energy goes a long way. Later, enormous amounts of energy produce only tiny increases in velocity. The closer the object gets to light speed, the more stubborn it becomes. It is as if the universe is pushing back. The mathematics behind this behavior reveals something extraordinary. As speed approaches the speed of light, the energy required to increase that speed grows without bound. It does not merely become very large, it becomes infinite. Infinite energy is not something that might exist somewhere in the universe waiting to be tapped. It is a signal that the process itself is forbidden. The equations are telling us that reaching or exceeding light speed is not just difficult, but impossible. Feynman was careful to explain that this is not a failure of technology or imagination. It is not that we simply lack a powerful enough engine. The problem is deeper. The universe assigns a cost to speed, and that cost becomes infinite at the limit. Nature enforces this boundary automatically, without any external rulebook. What makes this even more fascinating is that the increase in inertia can be understood without invoking mysterious forces. It follows directly from the equivalence of mass and energy. Energy has weight. This is not metaphorical. Energy gravitates, resists acceleration, and behaves like mass. When an object moves faster, its kinetic energy increases, and that energy contributes to the object's resistance to further acceleration. Feynman often illustrated this idea by emphasizing that mass is not a sacred, unchanging essence. It is a form of energy. The famous relationship between mass and energy tells us that they are interchangeable. Near light speed, this interchangeability becomes impossible to ignore. Energy poured into motion does not disappear. It accumulates in a way that makes further motion increasingly costly. This explains why light behaves differently. Light has no rest mass. Photons are pure energy in motion. They do not need to be accelerated from rest, because they are never at rest. They exist only at the speed of light. Because they have no rest mass, they do not experience the infinite energy barrier that massive objects encounter. They are born at the limit and remain there. For massive objects, however, the situation is very different. They start with rest mass, which means they have an intrinsic resistance to acceleration. As they gain speed, they also gain kinetic energy, and that energy adds to their inertia. The faster they go, the heavier they effectively become in terms of resistance to acceleration. The universe does not allow them to shed this resistance. From a documentary-style perspective, this reveals a deep economy in nature. The same principle that explains why mass and energy are equivalent also explains why light speed cannot be reached by massive objects. There is no need for separate rules. One idea does all the work. This is the kind of simplicity Feynman admired. Another crucial aspect is that this infinite barrier is smooth. There is no sudden wall or abrupt stop. As speed increases, resistance increases gradually, but relentlessly. This makes the limit invisible at low speeds and overwhelming at high speeds. It is only when we push nature to its extremes that the true structure becomes apparent. Feynman pointed out that this behavior also protects causality. If energy could push objects past light speed, then cause and effect could be reversed in some frames of reference. The infinite energy requirement prevents this from happening. By making faster than light motion impossible for massive objects, the universe preserves the logical order of events. This also reshapes our understanding of power and progress. In everyday thinking, more energy always means more capability. But here, more energy leads to diminishing returns. Beyond a certain point, energy no longer buys speed. It buys inertia. It makes the object harder to move, not easier. This inversion of intuition is one of the most striking lessons of modern physics. Feynman enjoyed emphasizing that this is not an abstract mathematical trick. Particle accelerators around the world demonstrate it daily. As particles approach light speed, engineers can pour enormous amounts of energy into them, yet their speed barely changes. Instead, their energy and momentum increase. The machines confirm exactly what the equations predict. What collapses the mind is realizing that speed is not the ultimate measure of motion. Energy and momentum become the more meaningful quantities. Near light speed, talking about going faster loses its usual meaning. Motion becomes less about velocity and more about how much energy is bound up in the system. This insight forces a shift in perspective. Instead of imagining an object racing faster and faster through space, we must imagine energy piling up, thickening the object's resistance to change. Space allows motion only up to a point. Beyond that, it demands an infinite price. Feynman's deeper message was that limits in physics are often signs of structure, not failure. The infinite energy requirement is not a flaw in the theory. It is a clue. It tells us that the universe is built in such a way that certain questions have no physical meaning. Asking how to push a massive object beyond light speed is like asking how to draw a square circle. The rules that define the concepts make the request self-contradictory. In the end, the inseparability of energy and mass near light speed reveals why the limit is absolute. Speed is not free. It is paid for with energy, and the cost curve rises until it becomes infinite. Light speed is not guarded by an external barrier, but by the internal logic of energy itself. What Feynman uncovered is that the universe does not need to say no explicitly. It simply makes the price impossible to pay. The idea of cause and effect feels so obvious that we rarely question it. Something happens, and then something else follows. A switch is flipped, and a light turns on. A stone is thrown, and a window breaks. This order feels absolute, built into the very logic of existence. Richard Feynman insisted, however, that this sense of order is not guaranteed by philosophy or common sense. It is guaranteed by physics, and more specifically, by the speed of light acting as a fundamental limit. Without that limit, the very notion of cause and effect would dissolve. At first glance, it is not obvious what speed has to do with causality. Cause and effect feel like logical ideas, not physical ones. But in the real universe, causes influence effects through physical processes. Information has to travel, forces have to propagate, signals have to move from one place to another. None of this happens instantly. The speed of light is the maximum speed at which any influence can travel. It is the speed at which reality communicates with itself. Feynman emphasized that this is the key point most people miss. The speed of light is not about how fast light beams move through space. It is about how fast the universe can transmit cause into effect. Every physical interaction, whether it involves gravity, electromagnetism, or nuclear forces, respects this limit. Nothing can influence anything else faster than this speed. To see why this matters, imagine a universe with no such limit. In that universe, information could travel infinitely fast. An event in one location could instantly affect another location, no matter how far away. At first, this might sound convenient or even magical, but when you examine it carefully, it becomes disastrous. The problem appears when motion is involved. According to relativity, different observers moving relative to each other disagree about the timing of events. This disagreement is not a flaw. It is a measured and unavoidable feature of reality. If information could travel faster than light, then there would always exist some observer for whom the effect appears to happen before the cause. What one observer sees as a signal being sent and then received, another observer could see as the reception occurring before the signal was ever sent. Feynman pointed out that this is not a philosophical paradox. It is a physical contradiction. If effects can occur before causes, then the universe loses its ability to define what it means for something to happen. You could, in principle, send a message to prevent the very action that caused the message to be sent. Logic collapses not because humans are confused, but because nature itself becomes inconsistent. The speed of light prevents this from happening. By limiting how fast information can travel, the universe ensures that all observers agree on the order of causally connected events. They may disagree on the exact timing, but they will never disagree on which event caused the other. Cause always comes before effect in every valid frame of reference. This protection is built deeply into spacetime. Events are separated not just by distance and time, but by something more fundamental, whether they can influence each other. The speed of light draws a boundary around every event, defining which other events can possibly be affected by it. Outside that boundary, influence is forbidden, not discouraged, not delayed, but fundamentally impossible. Feynman loved the elegance of this idea. The universe does not need a separate rule to preserve causality. It only needs a speed limit. Everything else follows automatically. Space and time arrange themselves so that this limit is never violated. This also explains why faster, then light motion is so dangerous to physics. If a massive object could travel faster than light, it would carry information with it. That information could be used to send signals into the past from some observer's perspective. Even if this seems abstract, the mathematics is unambiguous. Faster, then light motion and backward time travel are two sides of the same coin. Feynman made it clear that the universe avoids this problem not by clever bookkeeping, but by brute consistency. It simply makes faster, then light motion impossible. The infinite energy barrier near light speed is not just about mechanics or mass. It is about protecting the logical structure of reality. Another subtle point is that causality is not enforced locally by objects deciding to behave properly. It is enforced globally by the structure of spacetime. Even particles that exist for a fraction of a second obey this rule perfectly. They decay, interact, and transform in ways that never allow effects to precede causes. The speed of light acts silently in the background, ensuring this order without ever announcing itself. From a documentary-style perspective, this reveals a universe that is consistent at a deep level. It does not rely on special cases or exceptions. The same limit that governs light beams also governs thoughts transmitted by radio waves, forces between particles, and the evolution of stars and galaxies. Causality is not layered on top of physics. It emerges from it. Feynman often warned that when people talk about breaking the light speed limit, they are usually thinking only about motion, not about information. But information is the real issue. Even if some hypothetical object could move faster than light without carrying information, it would still challenge the structure of spacetime. The universe does not allow such loopholes easily. What makes this insight so powerful is that it reframes the speed of light as a guardian of meaning. It preserves the idea that events have reasons, that actions have consequences, and that the universe unfolds in a coherent sequence. Without it, physics would still have equations, but those equations would describe a world where prediction and explanation lose their foundations. Feynman's deeper message was that limits in nature are often signs of necessity, not restriction. The speed of light exists not to frustrate exploration, but to make existence possible. It keeps time from looping back on itself in destructive ways. It ensures that the story of the universe has an order that can be followed. When we say that cause and effect depend on the light's speed limit, we are saying that the universe cares about consistency more than convenience. It allows strange effects like time dilation and length contraction, because those preserve causality. It forbids faster than light influence because that would destroy it. In the end, what collapses the mind is realizing that causality is not guaranteed by logic alone. It is enforced by physics. The speed of light is not just a number measured in experiments. It is the silent rule that keeps the universe from contradicting itself. Remove it, and reality stops making sense. The most unsettling idea Richard Feynman pushed people to confront was that the speed of light is not a technological ceiling waiting to be broken, nor a cosmic rule enforced from the outside. It is an internal feature of reality itself. Nature is wired in such a way that this limit emerges automatically, without permission, without exceptions, and without negotiation. To understand this is to realize that the universe is not just a collection of objects moving around in space, but a tightly organized system whose deepest rules determine what can and cannot exist. Human thinking is naturally shaped by engineering problems. When we see a limit, we instinctively assume it is provisional. Mountains can be climbed, oceans can be crossed, and sound barriers can be broken. For centuries, Speed limits have always been temporary, waiting for better tools. Feynman warned that this mindset becomes misleading when applied to fundamental physics. The speed of light is not like the speed of a horse or a jet. It is not a challenge set by nature to be overcome. It is part of the definition of how the universe operates. What Feynman uncovered is that the laws of physics are not written on top of space and time. They are written into them. The speed of light is one of the constants that defines this structure. Once this constant exists, everything else follows. The behavior of particles, the flow of energy, the propagation of forces, and even the sequence of events are all shaped by it. Remove or alter this limit, and the entire framework collapses. This is why attempts to imagine surpassing the speed of light always run into deeper contradictions. It is not just that equations stop working. It is that the concepts those equations describe stop making sense. Motion, time, distance, energy, and causality all rely on the same underlying structure. The light's speed limit is a load, bearing pillar. Take it away, and the building does not merely crack, it disintegrates. Feynman emphasized that nature does not explain itself in terms of human goals or desires. The universe is not designed for convenience or progress. It simply follows its own logic. That logic turns out to be astonishingly strict. The same rules that allow atoms to exist, stars to shine, and matter to remain stable also enforce the speed limit. There is no separate compartment where faster than light exceptions could hide. One of the most profound aspects of this wiring is that the limit does not feel absolute at low speeds. At everyday velocities, space seems rigid and time seems universal. The universe appears forgiving, flexible, almost casual. This is an illusion born of scale. The deeper structure only reveals itself when pushed to extremes. Feynman loved this because it showed how nature hides its most important rules behind familiar appearances. As speed increases, the universe responds not by breaking, but by adapting. Time slows, space contracts, energy piles up, and inertia grows. Each of these responses is automatic. There is no central control deciding when to activate them. They are consequences of the same underlying equations. The closer an object gets to the limit, the more violently these effects assert themselves, until further progress becomes impossible. This is what it means to say the universe is wired for the limit. The resistance is not external. There is no wall. There is no final collision with an invisible barrier. Instead, the very act of trying to go faster changes the conditions of motion. The universe reshapes itself in response, making the goal unreachable. Feynman often pointed out that this kind of limit is very different from anything in everyday life. In engineering, limits are imposed by materials. In physics, this limit is imposed by meaning. Beyond the speed of light, words like before, after, here, and there lose their universal definitions. The universe is not willing to pay that price. Another crucial insight is that this wiring is deeply democratic. It does not matter what the object is made of. Can you provide independent confirmation of your client's federal employment, or how clever the design? Protons, electrons, spacecraft, and signals all obey the same rule. The universe does not negotiate based on scale or intelligence. The limit applies equally to everything with mass and information. This universality is what gives the limit its authority. If it were a special rule for certain particles or certain forces, it might feel arbitrary, but it appears everywhere, in every interaction, in every experiment. It is written into the equations that describe electromagnetism, gravity, and quantum fields. It is not an add-on, it is a foundation. Feynman also stressed that this does not make the universe simple in a boring way. On the contrary, this single limit gives rise to extraordinary richness. Time dilation allows particles to survive longer. Energy, mass equivalence powers stars. Causal structure gives rise to history and memory. The speed of light does not constrain complexity, it enables it. What collapses the mind is realizing that many of the things we take for granted depend on this wiring. The fact that the universe has a consistent history, that information cannot arrive before it is sent, that physical laws work the same everywhere. All of this relies on the existence of a maximum speed. Without it, reality would not just be strange, it would be unstable. Feynman resisted the temptation to dress this up in mystical language. He did not say the universe wants a speed limit. He said the universe has one because, without it, the equations describing nature would contradict themselves. Nature is not sentimental, it is consistent. This perspective also reframes the idea of discovery. There is nothing hidden behind the speed of light waiting to be unlocked with enough ingenuity. The limit is not guarding a secret realm of faster physics. It is telling us that the map ends here because the territory itself ends here. Beyond this point, the questions we are asking no longer correspond to anything real. Feynman often reminded students that physics is not about imagination alone. It is about disciplined imagination, constrained by experiment and logic. The speed of light is one of those constraints that imagination must respect. Ignoring it does not make ideas bold, it makes them meaningless. From a documentary-style view, the universe appears almost self-aware in its consistency. It does not allow loopholes that would undermine its own structure. Every attempt to bypass the limit encounters the same response. Space and time rearrange, energy requirements explode, and causality stands firm. The universe closes ranks around its deepest rule. The most humbling realization is that this rule was not designed for us to understand. It simply exists. We stumbled upon it by measuring light, questioning assumptions, and following equations where they led. The collapse of intuition that follows is not a failure of the human mind, but a sign that we have touched something fundamental. In the end, what Feynman uncovered is that the speed of light is not a boundary at the edge of physics. It is the spine of physics. It holds the universe upright. To understand this is to see that reality is not infinitely malleable. It has a shape, and the speed of light defines that shape. Once you see this, the limit no longer feels frustrating. It feels inevitable.